Stop and then restart our recording. Okay, so Raghu Kancherla is now going to speak to us. Let's see. I'm sorry, I'm trying to catch up with a couple of details here. Are you ready to present? I see Fahad Khan is there.
Yes, hi everyone. Raghu, we can't hear you if you.
Can you hear me now?
Yes, we can hear you now.
Okay.
Okay.
Hello everyone.
Please carry on. We can hear you just fine, and go ahead and start. And I'll remind everybody to place questions you have in the chat. Thank you.
Okay. Hello everyone. My name is Raghu Kancherla, and I'm a postdoc scholar currently working at Center for Advanced Turbo Machinery and Energy Research, University of Central Florida. We also have my colleague, Dr. Fahad Khan, who will be sharing half of this talk today with me. And I would like to thank our co-authors, Javier Gioia from Office of Research Operations, and Professor Vasu from Department of Mechanical Engineering, UCF. We also would like to acknowledge and thank Department of Energy and Microsoft for partially funding this work. And special thanks to Rick Friedman for giving all the support from Azure for us to carry over this research on Azure HPC. This is the outline of our talk. This talk is divided into two parts. In the first part, I'll be talking about some introduction to the reacting CFD, and then I'll talk about what is the need of HPC environment for reacting CFD simulations. Our prime focus here is supercritical CO2 combustion. So this is a little more complex than a regular reacting flow simulation. So I'll talk about the importance of supercritical CO2 combustion, and then I'll talk about what are the benefits of cloud HPC, especially for this CO2 combustion research. Finally, I'll present some of my results, and then I'll make a comparison between our on-site cluster with Azure HPC. In the second part, Dr. Fahad Khan is going to talk about various challenges and pain points and experiences that we came across while deploying cyclocloud server and connecting it with our UCF infrastructure. And then he will also talk about various challenges that we faced in order to run a successful CFD simulation on Azure HPC. With that, an introduction to reacting CFD simulation. In any engineering design, four factors are critical. They are safety, accuracy, durability, and economics. Whenever we are developing a new product or we want to bring it to in commercial scale, we have to do rigorous testing in order to make sure that all these four factors are satisfied or not. When we are developing a new design, a new product, we will have a huge design space. For example, if I'm designing an aircraft, there can be various parametrics, huge parametric space for such as length of the aircraft, or shape of the wings, and curvature on the wings, and the location of engine. So in this way, we can have hundreds of parameters that we need to look into. And it is practically impossible to do experiments on a prototype or model, even in lab scale, on these various different configurations. Therefore, computer simulations play an important role in the initial design in order to eliminate unwanted design space. Therefore, just a background about CFD. In computational fluid dynamics, CFD, we discretize the whole domain of interest into various small cells. Based on the accuracy that we expect, we can have thousands of cells to millions of cells. And in each cell, we solve partial differential equations that governs the physics of that particular problem. That means if we have millions of cells, then in each cell we'll be solving those partial differential equations. And then if you have a million time steps, then at each time step we are solving all the equations. So they're computationally very intensive. A small introduction to what is non-reacting flow and reacting flow. Airflow on an aircraft is an example for a non-reacting flow. We all know that air has nitrogen and oxygen present in it. When the air flowing on aircraft, it may change its temperature or pressure, but nitrogen and oxygen within the air are not going to react. Whereas if you look at the engine, in engine we will have a fuel and oxidizer. They both react and then release tremendous amount of heat energy. In the process of releasing tremendous amount of heat energy, it also, I mean, the reactants are going to transform into products. So this is the difference between reacting flow and a non-reacting flow. When you see these two in terms of CFD simulation, here we have 5 parameters: density, velocities in 3 directions, X, Y, and Z directions, and then whether you need pressure or temperature. So we need these 5 parameters in order to fully analyze any non-reacting flow. So if you take a CFD simulation, then we actually have to solve 5 different partial differential equations in order to achieve these 5 parameters. Whereas when it comes to reacting flow, along with these 5 parameters, we have to solve another n number of equations. What is this n? This n represents number of species in combustion or the reaction. So for simple fuels like methane, we can have around 50 species present. Then the total number of equations will become 50 plus 5, 55 total. That is for a simple fuel like methane. And when you go to a complex fuel, then we can have even thousands of species. Therefore, non-reacting flow simulations are computationally very, very intensive. And then on top of that, these equations will have a non-linear source term. So whenever there is a non-linearity in source term, then the equations are going to be very, very stiff. We need a very accurate algorithms in order to capture those gradients. And obviously the simulations will take more number of iterations in order to reach the convergence point. And also there is a coupling between one equation to another equation. They are highly coupled. For example, how CO is carbon monoxide formed in a reaction is also depends on how CH4 is getting destroyed or how CO2 is getting produced. In that way, each and every species production or destruction, they are interrelated. So physics wise, reacting flow has more amount of physics that we need to solve. So based on the level of accuracy, we expect these reacting flows computations requires massive memory and not possible for to run on a single CPU. Therefore, we always need HPC environments. So here I want to stress one single point. Even a non-reacting flow simulations require HPC environment, where a reacting flow requires more intense, more powerful environment in order to carry this simulation due to its complexity of physics. Now, our prime interest is supercritical CO2 combustion. I'm going to give some introduction about that in the next slides. But this supercritical CO2 combustion is an example of reacting flow. On top of that, it has even more complex physics. So this is where we are currently applying, Azure Cloud HPC. And I'll be giving a brief introduction here in the next slide. So this is a layout of a typical supercritical CO2 power plant. We have a oxygen separation unit. This oxygen separation unit separates oxygen from air and then send it to combustion chamber. In combustion chamber, pure oxygen is going to react with methane or any other fuel and burns. So if here is a small simple chemical equations, when pure methane and oxygen react, it is going to give products CO2 and H2O. H2O is, we know that it's a steam. When you cool steam, we are going to change its phase, liquid phase. So in products, we can easily separate H2O from CO2. So that is a basic idea behind all this oxy combustion. We call, combustion pure oxygen. Now we know here the products that consist of CO2 and H2O, they go over the turbine and really generates power. The remaining stream, when we cool that, water is going to get separated, and we recirculate CO2 back into the combustion chamber. So this is the important here. So we are not going to release CO2 into atmosphere, but we will recirculate back into the combustion chamber. So that is a great idea behind this cycle, this power cycle. Based on current state of art, optimized conditions, this combustion chamber should be at a pressure of 300 bar. Just to give a notion of what is 300 bar is, it is something like 4 times higher pressure than a typical rocket engine. So pressure wise, it's too high. And we expect at least 95% of CO2 should be present inside the combustion chamber in order to have a very high efficiency for the cycle. So now what happens at these high pressures? As we increase pressure in a system, we are going to bring molecules close together. Generally, every molecule will have an electron cloud. Based on the nature of that molecule, we can have either positive or negative electron cloud around its nucleus. When we bring these molecules closer by applying a huge pressure, then these clouds may repel or attract based on its nature. Now, this is the more complex physics that we are adding on top of all reacting flow simulations. Now, because of these attractive or repulsive forces, all these transport, chemical and thermal properties are going to change in a in this environment. Therefore, we have to account this physics. So this is complexity, and some of the research reported that it will take approximately another 25% additional computational time in order to include this physics in the model. So here are some of the advantages why this technology is so important. Because we are reusing all the CO2 that is generated from the system, therefore we are capturing every single CO2 molecule, and without any additional cost. So that is a great benefit here. And then since we are not using nitrogen, when we are burning it with pure oxygen, there is no trace of nitrogen. We don't see any release of nitrogen oxides into environment. Therefore, it's a cleaner technology. And then here is the crust of this whole importance of this technology. Here is a comparison between a steam engine and a CO2 engine. At high temperatures, SCO2 technology is going to give additional 10% of efficiency. In energy sector, increasing even a single percent, 1% of efficiency of the whole plant is going to save billions and billions of dollars for the industry. And now this technology is promising a huge efficiency gain along with a cleaner environment. On top of that, here is a comparison between the size of the components. SCO2 turbine is typically like 50 times smaller in size compared to a equi-power steam turbine. That means a turbine which is of a one-story building that can be put on a small table. So that compact it will be. So it has a innumerable so many benefits. That's the reason many of the federal agencies and industries are giving prime attention to this to bring this technology into the market. And here is one demonstration plant which is existing in La Porte, Texas. They successfully constructed this SCO2 power plant and fired this engine on 18th of May, 2018 May, and they are commercializing it soon. Therefore, in order to compete, due to the importance of global attention of this project or this technology, in order to be competitive in research, there is a need of having resources like super fast HPCs and the HPCs which are available immediately after our request. So the such kind of environment are very, very helpful in order to be competitive. Here is a Microsoft Research Fellowship that is awarded to Professor Subith Vasu. to perform this particular research and to be competitive in this area. Here is some preliminary investigation that I'm going to do, that we have done recently. Ideally speaking, in combustion chamber, we are going to burn methane and oxygen, whereas this is an ideal scenario. In the realistic case, we always will have some impurities adding and coming into combustion chamber. If you look at various sources of impurities, this oxygen separation unit, it may not be 100% effective. If you want to have 100% effective separation unit, it will be very, very expensive. So there can be some traces of nitrogen and argon present, and they can come into the combustion chamber. And then based on the source of origin of natural gas or methane, we can have some impurities present in it, like sulfur dioxide, sulfur oxides, or water vapors, etc., etc. They can also influence combustion. And then here I'm primarily talking about this third kind of impurity, that is impurities coming out of CO2. Now, I just said that in previous slides, we are going to recirculate CO2 back into the combustion chamber, so we are not releasing it to environment. If you look at always from the combustion chamber, there can be some carbon monoxide present, or some trace of oxygen present, or some trace of H2O present, and they can come back and recirculate into the combustion chamber. And the concentration of these impurities can keep on increasing over a period of time. When you continuously operate this closed loop engine for about a week or a month or a year, so the concentration of these impurities will keep increasing at every loop, and then it can completely alter the physics of combustion or the combustion phenomena inside the engine. So that is we are focusing in this research to identify the effect of those impurities. So here I'm making a comparison of 3 different cases. In first case, we have a pure CO2 coming back into combustion chamber. In next 2 cases, we have a small percentage of oxygen coming along with that recycled CO2. And in third case, I have small percentage of water vapor coming along with CO2. And we used a commercial tool called Converge and then performed large eddy simulations. These are high fidelity simulations. Coming to results, here is a counter plot of carbon monoxide. So CO is a very important intermediate molecule that comes in combustion, and that determines effectiveness of combustion that is occurring. Now, here you're looking at a cross section of engine. Pure CO2, you see that the flame is standing far from the injector. So if flame is close to injector, what could happen is it can damage, increase thermal stresses in the injector, and it can damage injector soon. But if you add little amount of O2 impurity, you see that this is actually coming back and affecting the injector inlet. And the same thing is happening even at H2O. So in this way, we can identify what is the effect of impurities on the combustion chamber or combustion chamber performance. Here is something what we're looking at the exit. By having small amount of impurity, we have significantly reduced CO emissions from the engine itself. Now, finally, a comparison between Azure and Stokes. Stokes is our on-premise cluster at UCF. One simulation, which took 3 days on Azure HBV2 nodes, it took around approximately 18 days to complete on our UCF cluster. So it is a significant gain on speed of computation speed. And then if you look at the latency, Stokes on an average latency is around 120 microseconds, and whereas Azure has around 4 microseconds. So this is a comparison just for a single simulations. And we can imagine, like, if you want to do tens of simulations, it is going to, you are going to be getting it very fast. We can do it very fast on a cloud environment like Azure cloud. So hereafter, Fahad is going to take and present his.
So Raghu, will I be able to, I think, request? I don't think I can request control. So
Okay,
maybe
I can change the slides for you.
Or maybe I can just share my own screen, because I think there'll be.
Yeah, that will be better.
Okay. Thank you. So is everyone able to see my screen, the slides?
Yes, we see it and we can hear you.
Okay, thank you. So I'll be talking more from a, let's say, a technical experience aspect of what kind of challenges might researchers, face if they're trying to transition their workload from on-premise to cloud resources. So when we, what were the objectives and considerations of the research team? So the basic consideration was, that they wanted a quicker R&D turnaround time with minimal changes to their workflow. What does this mean? So we have our on-premise cluster. It's UCF ARCC Stokes. The thing is, that you can quickly get your job scheduled there, but it has long execution time. So in this case, it was taking approximately 18 days to get the job done. The researchers will also have access to national clusters. One of them was as NERSC. But the point with these clusters is that generally there might be delays in when do you get your job scheduled. So for example, they have experienced approximately at times 2 days to get their job deployed in those clusters. So Azure HPC, or HPC in the cloud, therefore provides this, ability to have on-demand resources. You can control the runtimes with the type of nodes or resources you're using. But obviously the trade-off is cost over here. What do they mean by minimal changes to the workflow? So this means, that the researchers the way they upload data to the machines, get the data back, or the type of scripts they are using to submit their jobs. For example, they were using Slurm scripts, So why is this important? Because Azure, for this, has you can do HPC 2 ways on, Azure. One is through Azure Batch, good for HTC and also HPC workloads. But the other thing is they have this cycle cloud, through which you can set up clusters such as Slurm, PBS, or different kind of things. So the idea was, to set up a Slurm cluster for the researchers. So before I move ahead, I just want to also make sure that the audience of the researchers, they understand, for getting these kind of things done, sometimes multiple teams are involved. So from a perspective of, UCF, the first thing is the researchers, the research lab, they were responsible to run their HPC scripts and simulations, but were also responsible for deploying the Azure resource group, any VMs, clusters, storage, those kind of things. And once they've deployed it, they were also responsible for, cluster and server management and the cost management. This cluster server management is important because generally, with on-premise resources, you always have a sysadmin or a team of, let's say Linux experts that handle these kind of things. But if you're a researcher, you'll have to, dabble into technology yourself to, get a couple of these kind of things resolved. The other thing is, we UCF Grid, I'm a part of this team. So I'm basically, my role at UCF is a research cyber infrastructure facilitator. So we had the role of research facilitation. We served as a liaison between various teams and resources. And at one point, we also started to, practically, support the deployment of the Azure cloud and the HPC, for the HPC. Microsoft was involved with us. They were primarily involved with consulting. The first phase of the consulting included, understanding what were the researcher needs, what type of nodes they might require for CFD, how do you provision them on Azure cloud, whether you want to go with Azure Batch or Slurm, and those kind of things. They also, I think, as far as I remember, they also gave us a demo on how we might want to use Cycle Cloud. In the second phase of the project, they provided us consulting for and support for HPC itself, because you might have these similar clusters working on premise, but when they shift to the cloud, they come with their own kind of problems. And one of the ones we faced was an issue where the application was unable to work with Slurm because of dynamic addressing. Then we had UCF-IT. UCF-IT is the overall cloud environment custodian at UCF. They were responsible for provisioning the Azure research group. Once this research group is established, that is where the research lab, the Cater research lab, and our team, started to deploy the clusters. UCF-IT is also responsible for, any VPN development or network support. And eventually, one more team in the university was UCF-ARC. That's our on-premise cluster. Because this application was already running on ARC, so we needed licensing server support from then management and access. The other thing to note is, that in UCF, you have the research network separate from, the enterprise network. And the ARC is hosted in this internet to network, and for the license server to communicate it, you needed these three tools to work together. for having this piece figured out. This R team also are eventually supporting us with container development. And this means that once you have that container, the jobs of the researchers, they'll be able to run them on both HPC on the cloud, while also on those on-premise clusters, or maybe one of those national clusters also. So for the project, we divide the project into, I see the project as being divided into 4 phases. The first phase is, where you assess researcher needs. As I talked about, the consulting demos. You also need to figure out application licensing. So for example, in this case, we were using Convert CFD, and there's a limitation, on whether you can, how many number of, how many parallel runs of the application you can have. For example, at any point in time, it can either be done on the on-premise cluster or the HPC cloud resources. Then, you also need to figure out in this first phase, who are the teams, who is going to, let's say, provide support for the cloud, for the Linux, maybe for the network piece, and who's going to do all these different kind of things. And in this phase 1, once we consulted with Microsoft, they told us, that I think it's the HPV2 series. I think each node has about 120 to 240 cores. They asked us to use that. They were specifically in the East US region. And UCFIT then, set up, to set up our resource group in that region. And there were some problems with that, but eventually it was done. Another part of this phase 1 is, cloud tools training. Both the researchers and ourselves, the grid team, we didn't have familiarity with Azure Cloud before this. And so we had to, go through some certain kind of training, to make sure that we understood what we were working with. So once the phase was done, we were set up with the resource script. The second part was, you deployed and configured the cluster. Now, we started with a Slurm cluster because that is what we wanted to do, but there were issues with the application, and we eventually had to set up a PBS cluster. I'll come to that issue later on the slides. And once we set up this PBS cluster, we ran some test workloads to see, we had a mock deployment, then we had the actual deployment and ran some test workload. And once it was all established, we moved into phase 3. Phase 3 is the current phase. The researchers are actually running their research workloads. And we had to do some performance analysis and tuning. Again, we needed some help from Microsoft from this. And going on from here, as far as I see it, the phase 4 should include, maybe some IO tests. For example, we want to maybe deploy a Lustre file system because cloud CFD simulations can be, IO intensive. So does it need maybe a Lustre file system, some cost optimization things, because the jobs do cost a lot. I think 8 hours of simulation are resulting in things around $500, so maybe you want to keep an eye on that. Some performance and scalability analysis, we haven't done anything like that. And I think the best thing is that will happen is the application containerization, that you can have a singularity container with Slurm, support for running this application. So what were the challenging aspects of this? I think one of the first challenges we had is this was the first time we were doing an activity with Azure HPC with multiple teams in launch. So it was important to find who were the right resources and persons and what will be the roles and responsibility and coordination among them. Figuring out this roles and responsibility might take time. Specifically if you have not done anything like this before. The other thing is, the training challenge. You need to identify what kind of skills you might want to run. In our case, there might be you might want to have some training on the cloud resources. You might want to familiarize yourself a bit more with Linux, and in this case, we also had to learn how to use the Cycle Cloud Azure solution for HPC, to configure containers. Another challenging aspect is finding technical support, So one is, pre-deployment, all these teams coordinate, but once the application is running, you might want support for, let's say, cluster performance tuning, that is HPC, sysadmin support, maybe OS patching or things like that. So for example, one of the things that happened was, I think I think the CentOS version on the cluster went out of date. And for that, we started to receive segmentation faults. And because we're not sysadmin experts, we didn't really know, what was happening. And that is where, we reached out to Microsoft and, they had a couple of sessions with us and we figured out how to, improve that, resolve that impediment. So I'll talk about some roadblocks and pain points that happened. One is this is important really, clarity of roles and responsibility. So when they started, there were a lot of these teams talking, but for example, if you don't really know who is maybe, let's say, serving as a liaison, or who is really going to, let's say, deploy the resources, there can be a certain weight on each other, and that can, lead to a loss of time, So this is important, realizing, clearly communicating, that who was responsible for, let's say, deploying those things inside the resource scope, who is maybe responsible for, just setting up the resource scope, and these different kind of things, and making sure, that if you don't understand HPC or Linux into that detail, so make sure you find resources or other people, who can help you with that. One of the other things that happened in the start that led to some, a loss of time, was resource group issues. So these HPV2 nodes were specifically available in the East US region. UCF has only network and VPN laid out in East US2 and Central US region. So initially it was provisioned in the East US2, but then we realized, that was a mistake because we didn't have that, those nodes were not available there in that region. And so we then sent the UCF IT, went out and then deployed the network in the right region with the appropriate HPC resources. We had license server connectivity issues, as I talked about, both networks being separate, the research network and the enterprise network. And UCF RTA and ARC had to figure this out, to establish that connectivity. We had some application issues with Convert CFT. It was not, so the thing is, that once you're working on the cloud, as soon as the jobs are finished on the nodes are deprovisioned. So somehow there was a certain way the names were being dynamically generated, and the Convert CFT application was unable to pick up those names. And for now, we have did shift to PBS, but the hope is to, maybe resolve, the hope is to resolve this with Slurm. Otherwise, there will be no point in having containerizing the application itself. And one last thing, happened was a faulty workload. We had a faulty workload. It was generating segmentation 9 and 11 faults. It was supposed to stop and the nodes deprovisioned, but the nodes kept on running, and I think that job ran for 8 hours, resulting in quite a lot of cost without any output. So from the pain points, the next thing is, what might you want to look at in terms of skill development? You might want to look at crowd practitioner skills. Azure has quite a lot of resources, and now they also have a specific training track for researchers. So instead of, looking at yourself, developing into, let's say, a whole Azure expert, you can just look at this track specifically. It assists researchers, what they want to do. And the other things we learned was, how to use Cycle Cloud for spinning up these clusters, and you might also want to learn how to manage these permissions, access, etc., from a researcher standpoint. The other thing is you might want to have a deeper dive into Linux because you'll be managing, patching the server applications themselves, there might be firewall permission issues, on your cluster, and you need to figure out, how you can use, Linux scripts to really figure out what is the problem. And one last thing is, from our own aspect, we had to translate our Slurm scripts to PBS, so that was also a small part of that learning. So from this, my conclusions, my advice generally would be, that if you're planning, you're doing, HPC on the cloud transition on engage with experts from the start. You don't need to reinvent the wheel. You can always find, you need to seek institutional resources for support. Microsoft is also available, for that support. They can provide you support for, what might be your best cloud solution. What is your best, how to best configure your HPC, and if there are any Linux issues also. You need to find these experts at the start. It saves a lot of time. The second thing is plan with realistic times. Now, institutional resources generally serve the collective in general, and individual support takes time. For example, each university might have their own ticketing system. If a problems come up, it doesn't generally, it might not be resolved generally in a day or two. Sometimes it takes maybe 2-3 weeks. So make sure you plan for this. You include time for possible technical service, shifting to other things or workarounds, as we had to do with PBS and maybe 1 or 2 more things. And also include time for training and familiarity with the sources if you're new to this. And one last thing is, for collaboration, communication is the key. Communication is the key. Be sure, if you are an institution that maybe has a research facilitator, reach out to them. Communication is key. Set clarity in terms of needs, roles, and responsibilities. Sometimes you might be sitting on, that somebody else will get your job done. Maybe they'll provision that cluster themselves, but you realize, eventually you have to do it. So make sure you have that clarity in terms of what are the needs and what will be the roles and responsibilities. And figure out, who needs to remove or assist any roadblocks that come across the way. So to acknowledgements, this work was partially supported by Department of Energy, the Microsoft Investigative Fellowship, and UCF. So thank you.
Oh, fantastic. Well, thank you both, Raghu and Fahad, for this really, really great comprehensive talk. You managed to answer a bunch of our questions as we were developing them over the course of the talk. So we no sooner would we come up with one than you'd be answering it. So this is great. It's a little bit past 12. So what I'd like to do at this point is, since we do have some questions to go over, but our typical, our agenda says 12 to 12:30 is a break / Q&A. So I wanted to, first of all, point out that this talk that we just heard is the second time today that we've sort of seen a slam dunk on high performance computing on cloud, which is one of the big, super desirable sort of cloud equivalencies. It's a central pillar of cloud being equivalent to on-premise. And so it's really great to see this implementation. And I also really appreciated your perspective, sort of speaking as researchers, not as IT pros or as developer pros, and the fact that you're able to adapt. And one of the things that's come up in these great case studies we've had over the last 3 days has been everybody has had the opportunity to pivot and get help from the cloud providers. And that I think keeps coming through as a really great, important theme in how we manage our cloud adoption by relying on the help we can get. And to that end, I wanted to point out that today at 12:30, when this break is over, we'll have our closing presentation by Gautam Nastala from AWS. So I want to encourage everybody, if you possibly can, to come back for from the break for that presentation, because I anticipate it will be really, really excellent and worthwhile. Let's see. So the case studies have been wonderful, and the vendor or cloud provider engagement has been great. We're going to take this break now, and if you guys can stay on the line, then we'll just continue with our microphones and encourage people if they want to put questions in the chat. And then, like I say, we have a little set of questions to pose to you here. Does that work for you?
Yes, thank you.
Okay, wonderful. So deep breath. Let me turn to these questions that we have here. The first one that I have here says, other than runtime and on-demand scalability, were there any particular cloud service, for example, GPUs that you needed to use? And then there's a follow-up. Do you have a sense of whether industry government partners would be willing to adopt this cloud workflow, especially if they have invested a lot of resources in on-prem? So it's kind of two questions. The first one is, what else did you need to use? And how do you see the adoption, the willingness to adopt?
So the first thing is, in terms of, we didn't need GPU support. So we have two clusters on premise. One is Stokes, one is Newton's. Newton is the GPU cluster, because this was running at, I believe, on Stokes already. So in that case, we didn't need any specific GPU support.
And that was the 18 days on Stokes, you said?
Yes, 18 days on Stokes. And 18 to 3 days, is like quite an improvement. Specifically, if conferences are coming there, you want to get those results out, and specifically, waiting for a long time to see, whether a simulation really did result in the kind of the hypothesis you were expecting, so that's great, one thing. The other things in terms of, I think, adoption of cloud, I think there are still, there are still, it's something that is still, I think, needs. So for me, putting all of the load on the researchers, why would they want to really, start learning Azure and all those kind of things, So the thing is, this needs to be figured out, that how much load you eventually want to put on researchers. They generally, want to work with the simulations themselves, So why would, let's say somebody who is let's say an expert in, let's say chemistry or physics, go outright, and learn all those IT technical skills. So I think that is one thing, that needs to be figured out. And the other thing is, I think it's how you put the cost models in the university. I was looking through, recently various cost models, and how they subsidize, on-premise clusters, those kind of resources, I think that's also important. So one of the things I felt is, that when they're modeling, when universities start thinking, in terms of cloud, so they think, that it's generally, you also need to consider, that it's not just the nodes that you're buying and working with, the building that you're hosting that in, all the electricity bills, all those things might be already being subsidized. So I think some of the technical cost analysis that I've come across, I don't see them as being very fair. But my point is, until it's realized, that basically cloud is just giving you a replacement of all of that infrastructure, that support, and those kind of things, So I think having more clarity of what really cloud solves and what burden takes away from you might make it easier for universities to adopt, cloud solutions.
Was it adequate for you to just have in mind this? We could potentially save ourselves a bunch of time and effort in order to sort of get the go-ahead to try Azure. What were the key factors that made you decide to leap forward instead of just staying with your cluster?
Setting up and staying with the Slurm cluster?
Yeah, exactly. With your on-premise, with Stokes, at some point you had to say, no, we've got to give the cloud a try. So I'm just curious if there was some like key deciders or incentives to justify that leap.
Yeah, I think Raghu, the researchers might be able to speak better to that, and Dr. Vasu. So Raghu, if you can. So
yeah, the key thing is like getting resources faster. Fahad has already showed in one of the slide. We were having access to on-premise cluster and a national cluster in ERSC. If I deploy a job on NESC, it used to take at least 2 to 3 days in order to job start running. So it is actually a waste of time, especially when if you are working on a technology that is competitive, and if you want to be competitive and do a good job, so it is always better to have better to have a very good cluster that immediately available for you. So that is a prime motivation, immediate availability of resources. That is a prime motivation for us to look into cloud HPC.
Okay, cool. And one of the things that I'm always curious about is leaving like an artifact. So if you were to, let's say, look back in time at yourselves starting this project, do you have any kind of bandwidth and interest in creating the document you would have wanted to read back then? Like just go directly to CycleCloud, or, learn this technology first and don't worry about that. Is there any kind of like artifact that you could hope to share with the community to help other people follow in your footsteps?
Yes, definitely. I think one of the things I realized is, that the on-premise cluster, versus the cloud cluster, though they're named the same thing, there's a Slurm or PBS, they might come with their own, small challenges, And for example, there might be small things, So for example, I think the InfiniBand nodes, the network they share those nodes, though they are structured to be secure and private, but they share, So you can, let's say, easily profile performance of your cluster, So for example, one of the things we did is we tried to look into recently in PERC, how you can do some profiling, performance profiling. It's not that straightforward on cloud resources. So that's one thing, you might want to figure out how to do those things. We also want to document this because there are small things that happen, you might want to keep a record of that small, but the other thing is, if I go back, and I would think, one of the things, I think I would also like to, see how well does Azure Batch work, without shifting to Slurm, So my feeling is, Azure Batch might have a shorter learning curve because there won't be that server management involved for CycleCloud. There won't be. So if I really want to say is, CycleCloud is more like a solution geared toward multiple researchers using HPC. And then you want to spin up a specific cluster that's linked with your on-premise cluster. Well, Azure Batch is specifically tailored for, I think, individual use cases. But because initially we thought, that might be a good idea, having a similar workflow, that containerization piece, we went with CycleCloud. But so I think yesterday I was looking, I did find, that there is something that Azure Batch does support Slurm. If that is the case and you can make it work with it, then that will make for a good container application for Azure Batch also. So I think in looking back, I think Azure Batch, I want to see how well it can do with Slurm. Yeah.
Okay, cool. Well, I think one of the things that we're hoping to do in CloudBank is to circle back with teams like yourself and try and sort of capture some of the wisdom in terms of what we can provide as a community resource for knowledge and just sort of learn from your experience. So that sounds like you're open to that, and that's really great. And then I guess the last question I'll ask is probably not easy to answer, but I'll just throw it out there, which is, do you have, just in terms of dollar cost, any kind of a sense of the comparative between going to Azure and staying with your local, acknowledging the huge advantage of only waiting 3 days for a job to finish instead of 18. I mean, that's ridiculously valuable. But I'm just curious if you have any kind of dollars to dollars sense of that cost trade-off.
So that is what I was alluding to. I'm not exactly sure of that. So because when maybe the reports inside the university, which I've seen, they consider costs specifically just, let's say, for the rack itself or the nodes themselves. They don't include the cost for those personals, maintenance, all those kind of things.
Right.
So, and I found some other and I don't think that's a fair comparison. I think that's not a fair comparison when you're considering cloud, because all those things are being managed for you. So right now I won't be able to maybe give a clear answer on that. I do think that cloud HPC on cloud can be cost prohibitive unless you're being funded by a very good grant. You have tons of money. So I think one of the things that needs to go, strategies that can bring down this cost, resource sharing maybe, so let's say those kind of strategies, how can you subsidize the cost? That can, I think that can also help with making HPC on the cloud more popular.
Yeah, cool. All right, let's see. There's one more question here that's coming in on my feed. It says follow up. Did your team build a prototype beforehand in any way to sort of explore things before you leaped in with the full?
Yes. So the first thing we did was a mock deployment. I had this MSDN subscription, and I tried to deploy a cycle cloud server just to see how that server works. 2 nodes that cannot be classified as HPC or that can use InfiniBand, just to make sure to see that whether that cluster works. That was the first thing. You don't really want to start running those high powered nodes because they are expensive. Once you start running them, they start costing a good deal of money. So I did that mock deployment. So for moving from that MSDN towards the actual resource script, there was, I think, one major. I think one was I was not using. I think I was using it as a managed resource or something, and when I shifted to the resource group for UCFIT, it had to use a service principle. So I think that is the only big change that was. Otherwise, you can go out and test cycle cloud and an MSDN description, and you can find maybe more. You can generally understand what that application is just from, I think, from a mock deployment.
Yeah. Well, I think that's one of the things, I emphasized this in our leadoff talk on Tuesday morning, that because the cloud providers have this sort of research orientation and they can make credits available, it's often possible to do that kind of early testing without having a big financial risk because the credits are available. So
we have also seen this, researchers really want, have some money in research credits. They're really happy, if they can have that, they can test that. I've generally seen then they do go for the solution. But so somehow making that easy for researchers to get the research credits, because I think while working with other providers, we've also seen sometimes getting those research credits might take some time. So having that quick access to research credits for, let's say, ML tools or other kind of tools also can learn to quicker adoption of cloud resources.
I think Subith wanted to make a comment on cost too. Subith, are you there?
Yes. Yeah. So thanks, Raghu and Fahad, for presentation. So in terms of the cost, as a researcher, we have 3 options, right? One is there are university managed clusters or high performance computing centers, so we can utilize that. And that is some universities have a cost that each researcher will have to pay. Other than that, most universities provide it free, but it has serious limitations like the ones that we have here. You saw that the speed wise 3 days versus 18 days, right? So that's a big difference. And the other option for us as a researcher is to utilize the Department of Energy or the Department of Defense supercomputers. And for those are very highly competitive process, and you have to write a proposal and they allocate time based on what is merit wise and other factors. And those are, again, you don't get to use it whenever you want. You're given certain allocations, and sometimes you may not be able to use it when you want. And so but those are very, very competitive, and people have to wait. So the third option is Azure type cloud cloud PC. So that is very cost effective, and you can use it anytime you want. So there's no wait time. So if somebody is looking for quick calculations results, it's the best option than relying on in times like COVID, for example. You cannot wait for your calculations to be done in like 2 years, right? So you need it immediately to provide answers. So that is an example. And again, that's my comment. So I find it to be incredible, the opportunity to utilize the cloud computing.
Yeah, I think we're in violent agreement on that. All right, well, let's do this. It's now 12:17. We're coming back in 13 minutes. Let's stop the recording at this point. And I'll say thank you again, Fahad and Raghu, for the presentation and the follow-up Q&A. That's been really great to be able to sort of continue into our break time with you and get some more elaboration. So super fantastic series of presentations, case studies, and we'll take next 13 minutes and come back and hear our final presentation from AWS. So thank you.